The CareFusion 3100 series goes beyond convention as the benchmark in high-frequency ventilation, changing the way clinicians around the world think about ventilation. The 3100A and 3100B high-frequency oscillatory ventilators from CareFusion empower clinicians worldwide with the performance needed for the treatment of acute respiratory failure. The 3100 gently inflates the lung, normalizing lung architecture while ventilating the patient with near dead space tidal volumes for the ultimate in low-stretch lung protection. Backed by the excellent service you've come to expect, the 3100 series delivers the performance you want when your patients need it the most. The CareFusion 3100 makes it possible to approach full recruitment of the lung while minimizing stretch injury. It does this using delivered tidal volumes equal to or below dead space volume. This video describes the theory of operation for the 3100 series. In addition, you will become familiar with the ventilator controls, displays and alarms, circuit setup, and operational verification and startup procedures. The following instructional video is meant only as a supplement to the operator's manual. You must be completely familiar with the operator's manual before attempting to use this device. HFOV theory. High-frequency ventilation is a generic term encompassing many types of ventilation techniques. Although they all employ high respiratory rates, there are very distinct differences between them. These differences can be best identified by examining their frequency range, pneumatic principles, and most importantly, the expiratory phase. While several techniques employ passive exhalation, similar to a conventional ventilator, high-frequency oscillatory ventilation, or HFOV, uses an active expiratory phase. This distinctive feature is what truly defines high-frequency oscillatory ventilation. The CareFusion 3100A and 3100B are very simple devices. These are essentially large CPAP generators with a piston diaphragm oscillator attached. This system allows the 3100 to gently inflate the lungs while superimposing oscillations to ventilate the patient. This diagram represents a simple schematic of the ventilator circuit. The bias flow enters the system and passes through the humidifier, where it is heated and humidified prior to delivery to the patient. The gas then continues through the circuit to the patient and then out through the exhalation valve. The variable restriction to the outflow of gas generates mean airway pressure, while the piston superimposes the ventilatory process. Controls, displays, and alarms. The 3100A is comprised of two parts, the head and the ventilator body. On the back panel, the blender cooling gas filter replacement record and the driver replacement record are provided to assist service personnel in the proper maintenance of the ventilator. The elapsed time meter indicates the total time in hours that the ventilator has been in use. This compartment houses a 9-volt alkaline battery, which powers an audible alarm in the event of power loss to the instrument. The adjustment points for calibration of the airway pressure monitor transducer are located here. You should refer to the instructions included in your service manual for this calibration procedure. The head of the ventilator may be turned 270 degrees for optimal viewing by the operator. To lock the head into place, turn the position lock clockwise. An external blender must be used with the 3100A oscillator. The DISS connection for blended gases is labeled breathing gas. This fitting accepts a 50 psi input from the external blender. An external oxygen analyzer should be used to verify the accuracy of the delivered fraction of the inspired oxygen. The connector labeled outlet to humidifier provides patient breathing gas to the inlet of an external humidifier. A second DISS connection is labeled cooling air. This connection accepts a 50 psi compressed air supply, which cools the oscillator. It's important to note that the absence of an appropriately connected cooling gas supply could result in the failure of the oscillator's linear motor. The front panel can be divided into 3 sections: controls and displays for mean airway pressure, high-frequency oscillation, and alarm package. This sets the continuous gas flow through the system and is used to establish the mean airway pressure. Although the ventilator has a maximum flow rate of 40 liters per minute, typical applications use flow rates of only 10 to 15 liters per minute for newborns and 15 to 30 liters per minute for children. Since the mean airway pressure is flow dependent, adjustments to the flow rate will affect the mean airway pressure range. The knob on the front of the instrument labeled Adjust controls the mean airway pressure. Manipulation of this control changes the inflation of the balloon valve on the expiratory limb of the circuit. This results in changes to the mean airway pressure. Mean airway pressure is utilized to establish lung volume and thereby directly affects oxygenation. High-frequency oscillatory ventilation strategies often refer to the decoupling of ventilation and oxygenation. These strategies are based on the assumption that the first priority is given to establishing adequate lung recruitment. In this example, a pressure-volume curve demonstrates that full lung recruitment is not achieved until inflation pressures have reached a significant level. Following this initial recruitment maneuver, adequate lung recruitment may be maintained at a significantly lower pressure. The primary goal of any positive pressure respiratory support strategy is to establish and maintain adequate functional residual capacity, or FRC. Since the primary architectural component of the lung is the alveoli, failure to establish an adequate FRC with an appropriate mean airway pressure will result in a poor response to HFOV. Initial settings for the fraction of inspired oxygen, or FiO2, may also affect the ability of the clinician to identify adequate mean airway pressure. If the FiO2 is arbitrarily increased to 100% upon initiation of HFOV, assessment of initial mean airway pressure may be underestimated. By increasing the FiO2 incrementally by 10 to 15% during the transition to HFOV, the relative effects of mean airway pressure manipulations are more readily recognized. Amplitude. An electronic control circuit driving a linear motor produces the oscillatory amplitude in much the same way as in a permanent magnet speaker. When the square wave driver has a positive polarity, it drives the electrical coil and the attached piston forward in the direction of the patient. This results in an inspiratory phase. When the polarity is negative, the electrical coil and the attached piston are driven in the opposite direction, resulting in an active expiratory phase. To activate the oscillator, press the Start-Stop button. The green LED will illuminate, showing the oscillator circuit is energized. The mean airway pressure must be greater than 20% of the set high-pressure alarm setting in order for the oscillator to activate. The oscillator may be stopped without complete loss of mean airway pressure. This allows for auscultation of the patient without the loss of lung volume. Piston displacement is controlled by the power control, which is a graduated 10-turn potentiometer. The small lever on the control is a lock. It is set by moving the lever down. To unlock the control, lift the lever before turning. The displayed amplitude is the peak-to-peak oscillatory pressure measured at the airway opening. It's important to note when observing the pressures that the pressure amplitude reported by the instrument is the sum of both the inspiratory and expiratory phases of the ventilator. It will be significantly attenuated at the alveolar level by the resistance of the endotracheal tube. The same mechanism can result in severe detriment to ventilation. As secretions accumulate in the endotracheal tube, airway caliber is reduced, resulting in a lower tidal volume. Clinical strategies for HFOV call for the initial setting for amplitude to be based on chest wall movement. This movement should be visible from the chest to the upper thigh. A frequency setting that is too high may result in an elevated PCO2 that seems refractory to significant changes in the amplitude setting. It's also important to rule out other possible causes for an elevated PCO2 before deciding on a final course of action. For example, a dislodged endotracheal tube or the need for airway suctioning could easily be the cause for little or no response to manipulation of amplitude. In this case, chest wall movement will either be diminished or completely absent. The piston position and displacement indicator provides the operator with information on the position of the piston relative to its mechanical limits and the control settings. Inspiratory time percent. The inspiratory time percent sets the relative duration of the successive positive and negative polarity voltages from the square wave driver. Since this parameter is set as a percent of cycle time, absolute inspiratory time is a function of oscillatory frequency and inspiratory time percent. For most applications, this parameter remains at 33%. In applications where the patient presents with refractory hypercapnia, in the face of maximum ventilatory support, increasing the inspiratory time percent may improve ventilation and may improve lung recruitment. The effect of increasing inspiratory time percent is most pronounced at lower frequencies, such as those found in larger patients. Use caution when increasing inspiratory time percent in patients needing longer exhalation time, as air trapping may result. Frequency. Typical neonatal applications utilize frequencies of 10 to 12 Hz, or 600 to 720 breaths per minute. Typically, larger patients require lower set frequencies. Unlike conventional ventilation, in which minute ventilation is expressed as frequency multiplied by tidal volume, minute ventilation for HFOV is expressed as frequency times tidal volume squared. It's important to understand this relationship since it demonstrates that even small changes in tidal volume may elicit a significant change in minute ventilation. As discussed in the previous section, altering the voltage to the linear motor by manipulating the power control directly affects the amplitude. Since a given power setting represents a specific electromagnetic force acting on the piston, the duration of the force is controlled first by the frequency and second by the inspiratory time percent. As frequency decreases, total cycle time increases, thereby increasing the duration of the time the force acts on the piston. This results in an increase in tidal volume. This means that the frequency behaves counterintuitively to conventional ventilation, and that decreasing the frequency will increase minute ventilation. Once an appropriate frequency is arrived at for a given patient, it usually does not change for the duration of therapy. Alarms. Thumbwheel controls are used to adjust the set maximum and set minimum mean airway pressure alarms from 0 to 49 centimeters of water pressure. The set maximum mean airway pressure will provide an audible and visual signal when the alarm threshold has been reached. If the alarm for the set minimum mean airway pressure is triggered, audible and visual alarms are activated. The audible and visual alarms automatically reset upon resolution of the fault condition. Activation of the backup mean airway pressure alarms will also trigger audible and visual alarms. These backup alarms are factory preset for greater than 50 centimeters of water pressure for the high alarm and less than 20% of the set high mean airway pressure for the low alarm. When these alarms are triggered, the oscillator will stop and the circuit pressures will be vented to ambient pressure. Bias flow will continue. Bias flow is maintained, allowing the patient the ability to breathe spontaneously at normal atmospheric pressure. Once an alarm condition has been resolved, the circuit must be repressurized manually by pressing and holding the Reset Power Fail button until the circuit pressure is at least 20% of the set high mean airway pressure alarm. The Alarm Silence push button silences all audible alarms for 45 seconds. Once activated, this button illuminates a yellow LED. The alarm silence will remain active for the full 45 seconds. The power fail alarm provides an audible and visual signal, indicating loss of electrical power to the ventilator. This alarm is also triggered when the ventilator is powered off. To silence it, press the Reset Power Fail button. These three yellow LEDs are caution indicators, with no accompanying audible alarm. This LED indicates a low source gas condition of less than 30 psi for either of the high-pressure gas inlets. The battery low LED means that the power failure alarm battery located in the rear panel of the ventilator must be changed. The oscillator overheated LED signals that the internal oscillator coil temperature has reached approximately 150 degrees Celsius. The oscillator stopped indicator means that the oscillator system is enabled, but the amplitude is less than or equal to 7 centimeters of water pressure. An audible tone will accompany this red indicator and will automatically reset once the alarm condition no longer exists. Circuit Setup Procedure. Attach the bellows water trap assembly using the 4 T-handle quarter-turn fasteners. Snap the water trap into the metal clip on the front of the ventilator body. Connect the circuit body to the central port on the bellows water trap. Snap the 3-cap diaphragm assemblies onto the valve bodies located on the patient's circuit. Attach the 3 color-coded tubes to their corresponding valve caps. Green to the mean airway pressure control valve, located on the expiratory limb of the circuit opposite the limit valve. Blue to the limit valve, located on the inspiratory limb of the circuit directly in front of the driver. Red to the dump valve, located near the middle of the expiratory limb of the patient circuit. Attach the pressure sensing line to the lower fitting marked airway pressure. Attach one end of the connection tubing to the part marked outlet to humidifier on the rear panel of the ventilator. The opposite end of this tubing should be connected to the inlet of the humidifier. Connect the bias flow tube from the ventilator circuit body to the outlet of the humidifier. Insert the chamber temperature probe into the port on the connector from the output of the humidifier. Connect the heated wire to the heater wire output from the humidifier. Insert the proximal temperature probe into the tapered opening near the patient Y. Use the cradle adjustment to maintain the proper circuit height and angle. The proper angle should allow condensate to run downward into the water trap. The filtered circuit. The filtered circuit for the 3100 provides filtration of gas from the inspiratory and expiratory limb using a HEPA filter. The setup of the 3100 circuit is essentially the same as the non-filtered circuit. The limit valve is placed on the dry side of the humidifier chamber. This ensures the filter stays dry so it does not have to be changed. The dump valve has been moved next to the control valve behind the expiratory filter. Special connecting tubing for filtered circuits is provided to account for these new valve positions. Place the inspiratory filter on the fitting next to the control valve and connect to the inlet of the humidifier chamber. Place the expiratory filter in the circuit. Position the lure fitting at the bottom and facing the 3100. Connect the drain tubing from the bottom of the filter to the lure fitting on the top of the water trap. As the dry filter becomes wet, you may notice a slight increase in mean airway pressure or amplitude. Pressures will stabilize once the filter is fully wetted. Decrease the mean airway pressure or power controls accordingly. Likewise, when a used filter is replaced, pressures may be slightly higher since the new filter is dry. Readjust pressures as needed. If the expiratory filter is no longer needed, the circuit ends may be connected directly. The expiratory filter needs to be changed every 24 hours to ensure safe operation. It may also need to be changed if the pressures rise due to secretions. The inspiratory filter does not need to be routinely changed. When changing the expiratory filter, having a second caregiver available to assist or manually ventilate if needed is advised. Due to risk of aerosolized contaminants, personal protective equipment such as gown, gloves, masks, etc. should be worn for this procedure or per hospital guidelines. Prepare the new filter by removing it from its packaging and place in an accessible place such as on top of the 3100 or a bedside tray. Disconnect the water trap drain tubing from the lure fitting on the bottom of the filter. Carefully disengage the filter from the circuit and set aside. Place the new filter in the circuit. Reconnect the water trap drain tubing to the lure fitting on the bottom of the filter. Ensure all connections are hand snug, but do not over-tighten. Reconnect patient if needed, and depress the reset button to pressurize the circuits and resume ventilation. The 3100A high-frequency oscillatory ventilator is now ready for the operational verification and startup procedure. The operational verification and startup procedure must be performed before using the ventilator. If the 3100A fails any part of this procedure, contact CareFusion Technical Support. Connect all source gases to the ventilator and turn on the main power switch. Ensure that the stopcock to the water trap is closed and the cooling fan at the rear of the driver enclosure is operational and clear of obstruction. Patient circuit calibration. To calibrate the patient circuit, locate the instruction label on the right side of the ventilator and follow these steps. Insert the stopper into the patient Y and adjust bias flow to 20 liters per minute. Set the maximum mean airway pressure alarm to the upper limit. Set the mean pressure adjust to the maximum setting by turning the control fully clockwise. Press and hold the reset button to allow the patient circuit to pressurize. It's normal for the battery low LED to illuminate when the reset button is pressed. The mean airway pressure should read 39 to 43 centimeters of water pressure. If necessary, adjust the patient circuit calibration screw, shown here, to achieve a mean airway pressure of 39 to 43 centimeters of water pressure. Caution should be used when performing this procedure, since excessive force applied to the screw will damage the ventilator. If this pressure range cannot be achieved, remove any humidifier and check the circuit for leaks or damage. Ventilator performance check. To carry out the ventilator performance check, follow the instructions on the label located on the top of the ventilator. Insert the stopper into the circuit at the patient Y. Set the bias flow to 20 liters per minute. Press and hold the reset button to allow the patient circuit to pressurize. Set the mean airway pressure to 19 to 21 centimeters of water pressure. Set the frequency to 15 and the inspiratory time to 33. Press the Start-Stop button to start the oscillator. Set the power to 6. When a stable amplitude reading is obtained, verify that the amplitude and mean airway pressure readings are within the range specified for your corresponding altitude. Refer to the chart located on the top of the ventilator. This concludes our presentation on the 3100A high-frequency oscillatory ventilator. Should you have any further questions, please contact your product representative or technical support at the telephone number provided in your operator's manual.